All right, we're starting this, or continuing on with this one. I don't know how much I missed, but basically we were at the point where we'd found the derivative, 6x squared minus 30x plus 24. We had factorized it. If I drag down, we'd factorized it and found that the stationary points where f dash x equals 0 is at x equals 1 and x equals 4. Then we actually subbed in, but we realized at the end, once we'd done that, what we'd done was we'd subbed into the original equation, which actually gave us the y coordinate for our stationary points, which is lovely. And if you were asked to sketch it, that may be a necessary thing to do, because you'll need the coordinate. So if it actually said sketch this with all points, like all critical points in there, then you would need that y value so that you can sketch those. That makes sense, doesn't it? But what we need to do, because we're trying to just find out the nature of these stationary points, we have to now substitute back in, but this time we're going to do it into the derivative so that we can find out if the gradient at these points is increasing, decreasing, or 0. Cool? Now, we already have a little table there that we're going to fill out. And we've got when x equals 0, f dash x equals something. When x equals 1, f dash x equals something. When x equals 2. Now, you should be able to fill out when x equals 1 straight away without a problem. F dash x equals, come on, 0. That's what we just did. That's where we got 1 because we worked out which ones when f dash x equals 0. Okay? So now what you do is you substitute 0 into f dash x. F dash 0 equals 6 times 0 squared minus 30 times 0 plus 24, which should give you an answer of 24. Then we do the same with, why did I put, with 2. So what we're doing is we're actually testing either side of our stationary point. We're testing to the left of it, we're testing to the right of it. So now we do f dash 2. 6 outside of 2 squared minus 30 times 2 plus 24. And I'll just do the answer over there. 6 times 4 is 24, minus 60 is minus 36, plus 24 would be minus 12. Is that all right? As long as I did those calculations correctly. I think I did. 24 minus 60 is definitely minus 36. Yeah, cool. All right. Now that's given us numbers. Do those numbers actually help us much? Do we care what the numbers are? That gives us the gradient at that point. But do we care what the numbers are? Yes. So at 0, it is positive 24, which means the gradient is... What's the gradient doing? If it's a positive, gradient's going up. Yeah? At 0, gradient is flat. And minus 12, what's the gradient doing? So what's the curve look like at that point? Looks like that, which means it's a maximum. It's a local maximum. Happy with that? That makes sense, doesn't it? Then if we go down to this next one, I've actually left these in there. We already did f dash 2 minus 12 and f dash 5. So we've gone, the reason they use 2 is because English, my third language. We used 2 because it is to the left of 4, okay, because 4 was the other stationary point. We could have used 3. Why didn't we use 3? Why did we use 2? Mathematicians are lazy. And we'd already done 2. So why not use it? Absolutely. Oh, I say it all the time. I mean, I get a lot of maths teachers and a lot of people who say, don't say that. That sounds really bad that you're saying we're lazy. It's like, another way of looking at it is every single inventor in the world ever was lazy. No one invented something to make it difficult, except Rube Goldberg. Okay, but they're cool. Okay? Yeah, it's fine. Rube Goldberg is cool. He knows it. We all know it. But most inventions are made to make things easier. We don't do things like this, like maths. We don't do it to make things harder. We really don't. It looks like it sometimes, but we are trying to make things easier. Okay? That's why formulas come in. Otherwise, why come up with generalized formulas that work all the time? Why does Pythagoras' theorem make it better? We could just measure every triangle, couldn't we? We could do that. Why did we bother coming up with a formula? Because it's quicker. It's easier. We're lazy. Laziness is not necessarily a bad thing. We like efficiency. How's that? That's probably the more politically correct way of saying I'm lazy. I use a remote control on my television because I'm efficient. All right, so we've done those. We've subbed them back in, and we've got that. Now, once again, we have a negative gradient, which means it's going. We have a 0, which means it's flat. And we have a positive, which means it's going up, which means we've got a happy face. We've got a minimum. Okay? So when you're describing those points, at x equals 4 is it was a max, wasn't it? And you probably should say local. At x, oh wow, I got that round the wrong way. Yeah, I'm gonna change that and go 1 and 4 is a local. That all right? That took a long time, but the reason for that is we needed to make sure that you guys know where you're subbing back into and why. What is it you're trying to get? The fact that we subbed it into the original equation first, which was wrong, was great because it gives you an opportunity to look at it and go, well, hang on, that didn't give us the nature of the gradient or the nature of the curve. That gave us the y value that relates to that x value, which means I have the coordinates for the points. Yay! Well, you don't actually need it in this particular question because it's only asking the nature, but see how I've got this lovely little Cartesian plane there. If I was now going to say, well, what I want to do is I want to sketch it, because the question says now sketch the thing with the critical points. Now, we haven't found the x or the roots of the equation. Okay, we haven't factorized the cubic to find out what the roots of the equation are. So to be honest, we've only got 2 critical points. Okay, we don't have the y-intercept, we don't have the x-intercepts. Cool? What we have is the critical points for the turning points. So let's plot them. So what are they? X is 1. And what was our y value when x was 1? When we substituted into the original equation? 4. So it's there. And we know from this that it's a maximum, which is great. Okay. Now what was the other one? It was when x is 4, y was what? Minus. Okay, so it's down here somewhere, right? And to be honest, if you're asked to sketch it, like I said, you only need your critical points. So you would have your x-intercepts, you would have your y-intercepts, and you would have these 2 critical points. Now, they don't have to be perfectly accurate. You can write on it, it's not drawn to scale. As long as you have marked in what their coordinates should be, then you're fine. It didn't say draw accurately. Okay, so we've got 4 and minus 20, was it? 23, sorry. Okay, and then, but you also know from the nature of it that it's a minimum down there, yeah? So you know the curve is going to look something like that. Cool? If you had all the other critical points, you'd be able to fix out where that is, because I'm not even vaguely saying that that's accurate. You'd fix that up, you'd fix that up, and you'd fix that up. Okay? It's a cubic, so you know you're probably going to have 3 roots. You might only have 1. You might only have 2, but you're possibly going to have 3. But that's something you'd work out. Okay? We haven't done that. We didn't need to, but you can do it. So actually finding the y coordinate of your stationary point is not necessarily a bad thing, and in a lot of cases you will be expected to do it so that you can sketch it. Cool? Awesome.